Welcome to this introduction to the Trace Structures tool, part of the Build Chain platform, which enhances structural transparency and resilience through 5 specialized modules. In this video, we focus on the Data-Driven Modeling module, which uses machine learning to isolate environmental effects from sensor data, enabling more accurate detection of structural anomalies and smarter building maintenance decisions. Module 1, Data-Driven Modeling, focuses on improving the interpretation of building monitoring data by separating environmental influences from true structural changes. The process begins by collecting reference weather and structural health monitoring data. A predictive model is then built to map environmental conditions, such as temperature and humidity, to expected building behavior. This model allows us to compare real-time measurements with predicted behavior, so that when discrepancies exceed a defined threshold, an alert is triggered. All data, models, and alerts are managed through the build chain knowledge graph, enabling traceable, consistent, and automated monitoring over time. Ready to explore the Trace Structures API? Head over to buildchain.ilab.shtaki.hu to get started. Then, go to the Data-Driven Modeling section to either start with a new model or load an existing one, or simply explore the tool using built-in demo data. Use the input loader to upload weather and modal data from your device or via the BuildChain API in formats like CSV or JSON. In this example, we'll load weather data, such as humidity and temperature, from Granada, along with eigen frequencies computed from operational modal analysis of IoT acceleration data collected at the Cultural Heritage Pilot Building in a selected reference period. Once uploaded, the tool displays feature names, data distributions, and summary statistics. Then just click Next to continue. In the exploratory modal analysis view, we examine how weather conditions, like temperature and humidity, affect building frequencies, our quantity of interest. You can explore these relationships using a correlation matrix by selecting whether to show parameter to parameter, parameter to frequency, or frequency to frequency correlations. You can also generate custom scatter plots by choosing any variable for the x and y axes, and optionally color the points by a third variable to highlight trends. While the overall correlations are not very high, a clear dependency of higher building frequencies on temperature is already visible. Once you've explored the data, click Next to continue. To train a data-driven model, we first configure 3 elements: the train test data split, the model type, and its hyperparameters. The interface allows you to set the training ratio, choose whether to shuffle data, and optionally fix a random seed for reproducibility. Available models include linear regression, polynomial chaos expansion, gradient-boosted trees, and deep neural networks, each with different settings. For this example, we'll keep it simple and select linear regression, which requires no additional hyperparameters. After training the model, we can evaluate its performance using accuracy metrics. Although the model doesn't perform exceptionally well, largely due to significant noise in the frequency data, we can still see that it captures important trends. Specifically, the model captures 1-0.74, about 26% of the standard deviation in the target variable. This corresponds to an R2 score of roughly 0.55, meaning the model explains about 55% of the total variance in the data. While not perfect, this level of performance is reasonable given the noisy nature of the frequency measurements. In the feature attribution step, we analyze how input features like temperature and humidity influence building frequencies. Start with global sensitivities by selecting the Global Sensitivities tab. You can compute the mean and variance of the output, then run a Sobel sensitivity analysis to understand how much each input, or combination of inputs, contributes to the variance in the results. For model-agnostic insights, compute average SHAP values, which show the most influential features across the dataset. To dive deeper into a specific frequency, select a COI component and compute detailed SHAP attributions and Sobel indices to see which weather features drive that frequency most. For example, when analyzing the second frequency, we observe that temperature change has the strongest influence among all weather variables. The SHAP B-swarm plot reveals a clear trend. The higher the temperature, the higher the frequency becomes. Switch to the Local Sensitivities tab to analyze individual predictions using SHAP waterfall plots, which show how specific input values shift the output from the expected value. This allows transparent, case-by-case interpretation of how the model behaves under different conditions. In this step, we subtract the influence of selected environmental features from new monitoring data to isolate potential structural changes. Using the input loader, we upload the monitoring dataset and apply the trained model to remove known effects. The result shows how the signal changes once environmental influences are filtered out, highlighting only the remaining structural behavior. The system compares new monitoring data to the reference range, highlights anomalies, and displays them in a table with their exceedance levels. As shown in the figure, the newly uploaded monitoring frequency data remains within the range of the reference period data. You can also review summary statistics and save all results locally or register them in the build chain knowledge graph for future tracking. The updating submodule uses Bayesian inference to estimate which environmental conditions could produce a specific building response based on user-defined targets and uncertainty margins. You can upload target values for the frequencies and the acceptable standard deviation to explore under what temperature and humidity conditions those frequencies would reach the desired values within a chosen standard deviation. This concludes our overview of the data-driven modeling module in the Trace Structures API. For more detailed guidance, examples, and advanced use cases, you can find the full documentation directly in the interface or at the Trace Structures platform website. We also invite you to explore the other modules, such as hybrid digital twinning, multi-building model updating, and earthquake and climate resilience analysis to discover how Trace Structures enables smarter, data-driven building management throughout the entire lifecycle.